Welcome to Introduction to Computer Architecture Lecture 2. I'm Simon Moore and today I'm going to tell you about digital systems design. The majority of commercial computer designs are designed using a clocked digital circuit technique, and that's what we've taught you in 1A Digital Electronics. That's what we're going to be covering in the ECAD labs. So digital means digital logic levels. So we use a low voltage, say around 0 volts, to indicate false, and a higher voltage to indicate true. So the logic level is discrete, as opposed to analog circuits where the actual magnitude, the voltage magnitude, determines the value. One of the great advantages of digital circuits is that they reject a lot of noise, and so you can precisely move discrete values through the system, and this is what we're used to programming against. Clocked, what does that mean? Clocking also causes time to become discrete, so that state propagates through the system in discrete time steps. And we tend to use D flip-flops to store state and control the flow of information through our circuits. And there's a figure there showing a D flip-flop with a bit of data coming in on D, one bit of data going out on Q. There's sometimes a reset signal coming in, and there is always a clock signal, and that clock signal may be triggered on the positive edge of the clock, for example. Setup and hold times are absolutely critical to such a device. So the setup time is the time the D input must be stable before the clock edge occurs. Okay, and that setup time is usually a positive value. In other words, the D input's got to be stable before the clock edge, and if it isn't, if the data and the clock change at the same time, then the flip-flop basically becomes unreliable. It goes metastable. The hold time is the time the D input must remain after the clock edge. And this is a little unusual in that actually in most circuits the hold time is negative. And that's usually needed to tolerate what they call clock jitter. So this is where you've got variance in the clock going into different D flip-flops. And if we imagine data going from one flip-flop to the next, every clock edge, basically the D input gets copied to the Q output on the clock edge. And if we didn't have a negative hold time, then we might violate the setup time for the next flip-flop in the chain, if that makes sense. Actually, ensuring that we meet the setup and hold times for the flip-flop is critical to the digital abstraction. And if we break those setup and hold times, then basically our circuit abstraction becomes false, and it just will be unreliable. In order to distribute the clock throughout the circuit, we use a clock tree, and here's a logical representation of a clock tree. We've got a whole series of buffers. The clock comes in on the left in this diagram. It then goes through a sequence of buffers, and those buffers actually will sort of increase in size. We don't actually need to amplify the voltage of the clock, but we do need to amplify the current, because we need to distribute that clock over some long wires, and so we need some big drivers to do so. We keep forking the clock off in order to distribute it all the way through to the leaf nodes in this tree. Of course, we've got a two-dimensional chip, so we actually use a H-tree structure, which is a space-filling curve, which aims to propagate the clock to every part of the chip so that the clock edge appears at the same time everywhere. And technically we say this has low clock skew. Okay, so we've got the clock edge coming in, propagating all the way through, and it propagates through this structure shown here. And the idea is that if we look at the time difference between the clock edge on the leaf nodes, that the rising edges and the falling edges should basically line up in time, i.e. very low clock skew. Turns out this is quite tricky to achieve, and the clock tree structures actually use all sorts of components to mitigate subtle variations across the chip, and all sorts of challenges that go beyond this lecture. But this gives you the basic idea. Let's remind ourselves how we designed state machines in 1A digital electronics, and how we can use modern techniques to actually make the design process a lot faster. So here's a simple example of a 2-bit counter. We've got the state transition diagram there, and every time the go input is 1, we advance to the next state, and when the go input is 0, we remain in the same state. So that's the requirement. So in 1A you would have taken those requirements and turned them into a state transition table, and here it is for you. We've got the input signal on the leftmost column, the current state in the middle column, and the next state in the right hand column. And there should be no surprises here. When the go input is 0, then the next state is the same as the current state, and when the go input is 1, the next state is the current state plus 1. You will have then taken that state transition table and coded it into Carnot maps or K maps in order to do Boolean minimisation. And here are the two Carnot maps for the two output bits in relation to the inputs the input go and the current state N0 and N1. And for N0, the next state is simply the current state exclusive or go. In the N1 case, it's slightly more complicated, and you will have done Boolean minimisation by basically drawing sausages around common state. So in this case we've drawn the sausages around the 1s, and we can see that see where the don't care terms are, or where we don't care on particular input variables. Anyway, that gives us the equation below, and I've done a slightly refinement using exclusive OR gates. You will then have taken your Boolean minimised design and turned it into a schematic using D flip-flops and logic gates as follows. Now we're left to actually implement it. Clearly the design approach taken in 1A digital electronics is very laborious, and we need to do better. Nevertheless, the 1A process did really help you understand what the fundamentals are, what Boolean minimisation is, and where you need don't care terms. Now we're going to turn to using a hardware description language, which is what you're going to use in the ECAD and architecture labs. So we're going to use the language System Verilog, which is very widely used in industry. And for the design example we've just looked at, we can actually turn those requirements into a simple if statement. So if go, n is n plus 1. Otherwise, n won't be changed. We then wrap that up into a System Verilog module, including a clock. So here we've got a module where the module itself is called counter 2-bit. We've got some inputs. We've got an input clock. We've got an input called go. And then we've got an output of type logic, which is 2 bits, which is represented by 1:0 of n. And that logic means that it can become a D flip-flop. Then in the main body of the module, we've got an always FF statement. And this always FF statement means that the subsequent instructions within the block are going to be clocked. And we've got a definition of where the clock is coming from in the form of at POSEDGE clock. So every clock tick, if go is true, then we add 1 to n. Otherwise, n doesn't change. So going from our system Verilog through to an implementation proceeds as follows. We start with our system Verilog files, including libraries of IP intellectual property. We can then just take that Verilog code and run it through a high-level simulator, and that's very useful to do an initial quick check to see whether the design should be functionally correct. If we then want to implement it, we go through the following steps. First, we synthesize the design. So this is analogous to compiling a high-level software language, but here we're taking our system Verilog text and turning it into gates. Once we've got it into a gate-level netlist, we then need to feed it to a place and route tool, and this basically arranges all the gates over our chip or field programmable gate array. That finally gives us a low-level laid out netlist with all the details of where all the gates are, where all the wires are, and so on. And actually we can do a simulation at that level, which is lower level than the HDL simulation, and in some sense it's more accurate representation of what we're actually going to build. The other thing we need to do is do some timing analysis. You'll remember that I said we needed to preserve things like setup and hold times for the D flip-flops, and the timing analysis will determine whether the circuit will operate correctly at a particular clock frequency. So that gives us a pass-fail and other timing information, and if it passes, then we can then take that low-level design and turn it into an FPGA image, or we could turn it into a design that we could send to a chip foundry to be fabricated. Final thing to note is not only should we input the Verilog into this, but we also need constraints like timing requirements and pin definitions. So the timing requirements will say things like what clock frequency we would like the design to run at. We might also specify what circuit area we're looking for, and also, if it's something like an FPGA, what signals go to which physical pins on the device. And we need all of these things in order for the tool to do something sensible. And to give you one example, if you fail when you're doing ECAD labs to provide the pin constraints file, then it may well be that the design will just, the tool will just assume that it can assign pins any which way. The other thing that the tools can do is look at what's connected, and it can do optimizations during place and route and synthesis. And if it realizes that signals aren't going to be used because they're not connected to any physical output pin in any way, then it'll just optimize it away. And so you can find out that if you don't have a pin constraints file, your entire design gets optimized to absolutely nothing, which is nice and compact, but doesn't do anything useful. During synthesis, we also do automatic optimization. So the Verilog files are compiled or synthesized into that low-level description, typically a gate-level netlist, and then a number of optimizations are performed. So we first typically do Boolean optimization, just as you would have done by hand, but using slightly more sophisticated algorithms. The tools can also do things like optimal state assignment. So if you've used enumerations to represent state machines, then the tools are allowed to determine what binary values should represent those states, and that's another form of optimization. The other thing they can do are things like retiming for timing closure. So if we've got an example circuit as follows, here we've got some function f where the output goes to a flip-flop, and then on the other side of the flip-flops we've got functions G and H. Well, imagine G and H just taking a bit too long, so that the output of H, that will presumably go to another flip-flop, can't meet the timing requirement. In other words, the path is just too long. Then what the tools can do is automatically look at moving G to the other side of that D flip-flop. And it can do so provided it can basically prove to itself that it is still functionally equivalent. Anyway, really the sort of take-home message is that there's some quite sophisticated optimizations that these tools can do, but sadly it does take quite a lot of time. So compiling some hardware, and particularly doing all the place and route, tends to take an awful lot longer than compiling some software. We then move on to place and route, sometimes called layout. The starting point is the netlist. It's a directed graph of components, gates and flip-flops and things linked by wires. And the place and route is the process of placing all those components into physical locations on the chip, or FPGA, and then routing the wires between these components to complete the physical netlist in the most optimal way possible. There are constraints applied to the place and route tool, so there are area constraints, how big we want it to be. There might be localization constraints. So for example, a wire might need to be connected to a particular physical pin going on and off chip. And there's usually timing and performance constraints. The automated approaches for place and route are highly effective, but are very time consuming for large designs and for large FPGAs. So the sorts of designs you'll do in the lab on a reasonable performance laptop, place and route will be under 5 minutes. But things that we do on the research side on much bigger FPGAs, place and route can take over an hour on even a very high-end workstation or high-end server. The constraints are absolutely critical to getting a correctly functioning design. For example, if the place and route tool isn't told what clock frequency you want to run at, it will do just whatever it thinks is best, and who knows what the timing characteristics are, and you're certainly not likely to meet the timing that you actually want. The other thing to bear in mind is the tools will give up as soon as they have met the constraints. Okay, so if you said you want the design to run at a slow clock frequency, as soon as it's managed to figure out a layout that will actually meet that requirement, it will stop because it's done. Therefore, if you then look at timing analysis, which we're going to talk about next, if you've asked for a design at a particular frequency, when the timing analysis runs, it may tell you, it'll run at a slightly higher frequency than that. But in practice, your design might run at a much higher frequency if only you told the place and route tool that's what you wanted. So let's look in detail at what timing analysis does. So given the physical netlist and a detailed physical model, it has to determine the longest combinatorial path in the circuit. And it uses the same constraint information as place and route, including clock frequencies and other physical requirements. And the detailed physical model for, say, a particular FPGA includes characteristics of circuits as temperature changes and what the sort of statistical variability is from one FPGA to another. And that's then used to determine what the maximum safe clock frequency of the design, so as to ensure that the setup and hold times of the D flip-flops are completely valid. And as I've just mentioned, it's not useful to determine what the maximum Fmax is. You need to change the constraints in place and route to see if the circuit will actually go faster. So once we've assumed that once we've actually analysed the design and ensured that the setup and hold times are met for our D flip-flops, that then determines whether the circuit will work correctly in the field. And so this timing sign-off is absolutely critical, and the tools you're using in the lab are commercial tools, and for commercial customers, the provider of those tools is willing to sign off on the numbers. In other words, if you go and produce a design, you put it out in the field, and you then discover that some number of the parts fail because actually there was variability, or some of the devices get too hot and they go too slowly, then you would have recourse and be able to go back to the company who provided those numbers. So in other words, if the timing analysis tool says that the circuit will run at that frequency, you can believe it will run at that frequency. Let's look at what an example of a critical path is. So here is the circuit that we had earlier, that we designed by hand. If we look at the D flip-flop Q outputs, then we have a path from N0 all the way through an XOR gate, an AND gate, an OR gate to the input of a D flip-flop. And so those paths are the longest paths in the circuit, and they will then determine what the clock frequency is of the design. We need to be able to deal with external inputs. So it could be some sort of external communication input, or even something simple like a push button pressed by a human. And these things are not going to be synchronized to our internal clock. And if we're not careful, this is going to break our clock to digital abstraction. If a changed input violates setup and hold times, then it's going to cause the D flip-flops to go into what's called metastability, where the output is neither a 0 nor a 1, and this can basically introduce all sorts of erroneous behaviour into our circuit. The way we resolve this is normally using a 2 flip-flop synchronizer depicted here. The idea here is that the external input comes into the first D flip-flop. It will get clocked. Now that first D flip-flop may go metastable. Okay, so we've got risk of metastability at that point. And the idea here is that we're going to allow time, say 1 clock cycle, for that metastability to resolve, i.e. the output of that first D flip-flop will eventually go to either a 0 or a 1. And then on the next clock edge, the data will get copied through by the second D flip-flop, and everything will be nice and clean. However, this is actually critically dependent upon the amount of time we allow for metastability to resolve, and also properties of that D flip-flop. And that can be wrapped up in a mean time between failure, an MTBF equation shown here. Now, I'm not going to worry too much about the details, but I don't want to make it clear that this is a real problem, and it is something that you could see even in your circuits when you run on the ECAD labs. So T is the time for the first D flip-flop to resolve. TOR and T0 are parameters of the D flip-flop design, exactly how the transistors are constructed and so on. And those determine how quickly the D flip-flop will attempt to settle into an either 0 or a 1 state. FD is the frequency of the data, and FC is the frequency of the clock. So obviously, looking at this equation, if the frequency of data change is very low, then that helps. The slower the clock frequency is, the better it is as well. If we look on the top line, then we've got this e to the power of t over tau, and this is absolutely critical. So if t is too short, then because it's to the power of e, we can very easily change the MTBF from being once in the lifetime of the universe, which is good enough for me, to say once every second. And this actually is a real problem. And I mean, I have seen things. In fact, I've even been an expert witness in a court case during corporate litigation, where basically they'd failed to ensure that metastability was going to be resolved properly and that the MTBF was a good, robust number. The FPGA tools you'll be using actually will recognise things like 2 flip-flop synchronizers and will do the design optimizations to try and make sure that, for example, the wiring between the first D flip-flop and the second D flip-flop is as short as physically possible in order to maximise T for you, which is nice of it. Before implementing our design, we always simulate it to check the functional correctness. Of course, circuits are inherently parallel, and we need to model the parallel changes within those circuits. However, typically only a small proportion of signals change every single clock cycle, so there's various optimizations that can be done within the simulator to ensure that only gates and other devices that have state changes actually get simulated on that clock cycle. And we tend to use a simulation approach called a discrete event simulation, where those updates are based on signal changes. We can actually simulate at different levels, as I mentioned earlier. So we could do high-level simulation of the system Verilog itself. So in which case we actually rapidly load the HDL code into the simulator without first doing any place and route or actually doing any synthesis. So at this point we've got no detailed information about gate and wire delays. However, the clock is modelled, so actually we can get cycle accurate simulation, assuming that you can actually do the synthesis under place and route and meet timing. There are, however, problems with this form of simulation, and in particular, the synthesis tool and the simulation tool may have slightly different semantic interpretations of the system Verilog. Unfortunately, the semantics of system Verilog are not all that well defined, and actually this can be rather problematic. So in industry, people often do high-level system Verilog simulations to begin with, and then they will synthesize the design through to gates, and then do a gate-level simulation to check that the gate-level version matches the abstract version. Actually, also in industry, they quite often have design styles, and they may avoid particular subsets of the system Verilog language which are known to be problematic, where there can be different semantic interpretations. And finally, as I said, you can do gate level simulation. So this is post-synthesis and place and route. So it's much more accurately reflects the real implementation. However, you've actually got to wait for the synthesis and the place and route. So basically take it all the way through to the details of the design before doing the simulation. And that can really slow down the design process. So we often don't do that. Now let's talk about the structure of an FPGA, a field programmable gate array, which is the device that you're going to use to implement your designs in the ECAD labs. So the ECAD labs have the Intel Cyclone 5 FPGA, and inside these FPGAs you've got a number of different reconfigurable blocks. You've got LUTs, or lookup tables, for arbitrary combinational functions of n inputs. You've got ALMs, which are adaptive logic modules, which are basically built up of LUTs and D flip-flops, plus some programmable wiring. And then at the next level in the hierarchy, you've got labs, which are logic array blocks, which are sets of ALMs. And there are also things called M-labs, which are supersets of labs. You've then got a hierarchy of programmable wiring, And all of this is intermixed, if you like, with things like BRAM, in other words, block RAM. So this is SRAM based memory that's distributed throughout the FPGA. And there are also digital signal processing blocks that do things like high performance multiplies. So if you actually do multiply in your design, it can go and use a DSP block without actually deriving the multiplier in terms of gates. And this means that the multiplier will be very quick because it's actually made out of hard logic, not reprogrammable logic. There are, of course, I/O devices, so input and output pins for slow speed signals and high speed serial signals. So a lot of FPGAs support things like Ethernet, SATA, PCI Express and so on. And in fact, things like Ethernet and PCI Express at their lowest level, they use very similar serial communication protocols. So they'll use things like 8B, 10B coding and other signaling, even though the higher levels of the protocol are quite different. They also, FPGAs have interfaces for DDR memories, in other words, high-speed DRAM modules. Now, if we look inside, we've got things like ALMs. So here's an example of an ALM from a Cyclone 5, and it's got 4 LUTs, each are 4 inputs. There's actually some carry logic and a carry chain to do fast addition to speed those up. And then it goes to 4 registers, or via multiplexers you can bypass any of those registers. And the output of that then goes to general or local routing. If we then look in a little more detail, so this is just actually another diagram showing an ALM, but actually in a bit more detail showing more the multiplexers and various other bits of wiring. But don't worry about the details. I just want to indicate that they're moderately complicated devices. And then if we zoom out, we've got the FPGA wiring itself. So we've got rows of labs. We've got local interconnect between those, and then we've got sort of longer distance interconnect that goes further on the chip. And note in this particular figure, the actual clock distribution is not noted, and that is on its own dedicated wiring. We then have digital signal processing blocks. So as I said, these include things like addition, multiplication and so on. And in fact, in the more recent FPGAs, so the newer ones than the Cyclone 5, these get even more complicated and start supporting floating point operations, for example. So an alternative to designing an FPGA is to design an ASIC. In other words, design the actual chip, so an application-specific integrated circuit or a full custom chip. This is where all the transistors and so on can be laid out to whatever design you want. The one-off design cost, as I mentioned last lecture, is quite high. So we've got things like mass costs as well as design costs. And so it tends to limit ASICs to high-volume product, just to recoup the one-off non-recurrent costs. Actually, in order to do test chips, there are various services that do multi-project designs. So this is where a mask for a large chip will contain several smaller designs, and this is useful for running test runs, so sort of amortize mass costs. While with an ASIC you can actually design every single transistor yourself, we tend to use libraries of standard cells, so gates, D flip-flops and so on, and then there are generators for things like memory blocks and other regular structures, and then there will be libraries of high-level components, including things like processor cores. And at the lowest level of the design is geometric layout. So actually, all the layers of every transistor and the layout of all the wires and so on. So it's quite detailed. and that's the sort of that geometric information is what you hand off to the silicon foundry to be fabricated. In this figure we've got a microscope image of an old Intel 486 processor, and this one's kind of useful because you can still make out some of the wiring in it. The block on the top of the diagram looks kind of random, but you can sort of see within that randomness that things are laid out in rows, and this is basically a design that's been done using standard cell. So basically there'll be logic gates and flip-flops, and they'll all have the same physical height, and it looks on this diagram that they've all been sort of laid on their side, and that will get automatically laid out and wired up. And you can see on the bottom part of this photograph that there are some very regular structures, and those will have been laid out either by hand or using scripts that lay out these geometric patterns. So let's summarise. Clock digital designs are very widespread commercially in industry. Preserving the clock digital abstraction requires careful low-level design. So much of that low-level design is actually taken care of by the FPGA manufacturers, so for the work you're doing in labs. So things like clock distribution networks are already laid out on the FPGA, and handling reliable high-speed I/O. Nonetheless, the designer still needs to ensure that their design meets timing requirements and handles asynchronous input safely to avoid metastability. FPGAs are widely used for low to medium volume product, and you're actually going to be using commercial tools. So you're actually we're going to give you a route through the tools so that you get an idea actually what it's like to do this stuff for real. And then finally, ASICs are used for large scale volumes, so where you've got large number of products being produced, and they become much more cost effective than FPGAs at high volume. And with that, I'd like to finish.